Always is a pleasure to be here in Morelia, but especially for this 10th celebration of CRIA. So I will talk today of some work we have been doing our institute, the Instituto Astrofísica de Andalucía, with Juan Manuel Mayen, who is my PhD student, and with Mayra Osorio, who is a former student of here, of the CRIA. And most of this work we have been made in some collaboration, mainly with Luis Rodriguez, with Susana, and with Paola. I will talk about high angular resolution observation of ammonia in two home molecular cores, and I will talk about three results. A result that we published a few years ago, another one who just have been sending to publish, and a third one that is still in progress. As Guido explained before, home molecular cores are small and dense and hot condensations, which are usually found in the vicinity of H2 region. This is the same example that Guido showed before. And these condensations have densities of the order of 10 to the 6 to 10 to the 8 molecules per cubic centimeter, and the temperatures average on the order of a few hundred K. Usually the observations are interpreted using constant temperature and density and these kind of parameters, but our work has been concentrated in trying to analyze these observations using kind of models that take into account variations in temperature and density inside the envelope. So we think this is a better approximation, particularly in these hot molecular objects where the gradients are important. So hot molecular cores is thought to be the precursor of H2 regions, and in fact they do not have ionized material except for some weak jets, which is probably a different mechanism, not photoionization. A big step in the knowledge of this kind of objects, I think it was in 1999 when Osorio, Lizano, and D'Alessio analyzed 4 prototypical home molecular cores, and they show that their spectral energy distributions can be well fitted by models of infalling envelopes with very high accretion rates. They derive luminosities, the order of 10 to the 4 to 10 to the 5 solar luminosities, masses of the envelope of about between 30 and 400 solar masses, and very high mass accretion rates of the order of 10 to the -3 solar masses per year. So in my talk, I will comment a couple of these objects, and I will show that not only the spectral energy distribution, but also the molecular emission in this case, the ammonia molecular emission, can be explained with this kind of modeling. So I will talk about the home molecular core near the J31 H2 region. This is a free map made with at 1.3 centimeter with the VLA, and this is the ammonia 4,4 transition. Home molecular cores are characterized by a high transitions, high excitation transitions. So his existence is the demonstration of that this is a hot object. So these are the data on this object. This is the spectral energy distribution of taken from that data at different frequencies. And note that many of these points are upper limits, because there is confusion. They are taken with poor angular resolution. And there have been observed with single dish of many ammonia transitions, but they are particularly interesting, this 4,4 ammonia transition made with the VLA with high angular resolution, 0.6 arc-second by Cesaroni and collaborators, because they are able to angularly resolve the core. So they are able to see how the ammonia emission changes as a function of distance to the center of the core. This is here in more detail. So they took circular rings around the central position on the core, and they averaged the emission in order to gain signal-to-noise ratio, and those are the spectra at projected distance from 0 to 15,000 AU. What is impressive of this source, this is not a prototypical homolecular core, because this is extremely extreme case. The high brightness temperature of the ammonia emission, around 100 K, the very high optical depth, because if the emission was optically thin, the ratio between the main line and the satellite lines of the ammonia is 1/60. So here the satellite lines have the same intensity as the main line, so it indicates a very large optical depth. And also the lines are broad, because these are in fact two satellite lines which are blended, which indicate that any kind of turbulent motion can be important. So our goal was try to reproduce in detail these spectra. We used the same kind of models that were used in Osorio, Lizano, and D'Alessio, and they are characterized by the collapse of the singular logotropic sphere, and there are several models, in fact, all a family of models that can fit the set, because, as I noted before, these are upper limits, so the spectral energy distribution is not well constrained. I cannot see easily, but this is the temperature as a function of the radius. This is the density as a function of the radius. This is the velocity, the infall velocity as a function of the radius, increasing towards the center. And this is the turbulent dispersion that goes up to 4 kilometers per second in this model, and larger in these others. I will show a bit about this family of models. Model 1 has a central mass of 25 solar masses, and an accretion rate of 10 to the minus 3, and a luminosity of 10 to the 5, and the mass of the envelope is more than 1,000 solar masses. So as a characteristic model of the remaining models, I will show this model 5, which has a smaller mass. All these are decreasing in mass up to 3 solar masses, and we were comparing how the predicted ammonia emission compares with the observations. We note that the modeling of the spectral energy distribution give us the central mass, the mass accretion rate, the density, velocity, and temperature, and velocity dispersion of the envelope. So the only free parameter we have to fit the ammonia emission is the ammonia abundance. So we tried it with different ammonia abundance, and models from 2 to 11 were not able and were not promising in fitting this, because if we use a small ammonia emission, the intensity of the main line does not reach the value of 100 K. And if we increase the ammonia abundance, you see here they have the same intensity as the observation, but if we need more, and if we increase more, the main line becomes lower, because the opacity is so high that is only seeing the outer parts of the envelope, which are cold. So it needs to penetrate inside the envelope to see the high temperatures and become higher. If we use the model 1, this is more promising, because with a small abundance it reaches a temperature of 100 K, and with large values of the abundance, the satellite lines are able to reach also 100 K, but we cannot fit both things simultaneously. Then we think in an additional factor, is that probably the ammonia emission, the ammonia molecules are frozen in those grains in the outer parts of the envelope where the temperatures are small, and they are released to the envelope in the central parts of the envelope where the temperatures are high. So if we use the simple equation of sand for an Anayamandola, and we use the physical conditions inside the core, we see that for these densities, at temperatures of about 100 K, the water is sublimated. So the ammonia molecules are probably released, and this means an increase of the ammonia abundance for regions above 100 K. So taking into account this factor, we try with different values of the minimum ammonia abundance and the maximum. Our constraint was that total ammonia abundance was the same was constant, but the gaseous phase and the solid phase were changing according with the Sanford and Yamandola equation. And so we play with several values, and we got this pretty good fit where we can fit the spectra at different positions as a function of the distance to the center. Using these same values that fit the spectral energy distribution and the VLA observations of the 4-4 transitions, we calculate the emission of the 1-1, 2-2, 4-4, and 5-5 observations that were single-dish observations. The fit is not always so good, but if we take into account the uncertainty in the observations, with the author says about 30%, so the fits are fitting within the observational uncertainties, because the uncertainty in this calibration in particular was pretty high. So we have that in this source, the apparently can be modeled pretty well using an spherical accretion source. Of course, the source has departures for spherical symmetry. In fact, it has a velocity gradient. In fact, in the center, there is a binary source, but it all indicates that the main dominant effect kinematically is gravitational inflow, because with a model of gravitational inflow, we are able to reproduce the spectral energy distribution and the ammonia emission as a function of the density to the center. There are already indications that this source is in an infalling object. Is the hourglass morphology of the magnetic field, which is expected in the gravitational protostellar collapse, that it pinches towards the center. And also there is this inverse Piscini line profile, which is the emission line. I think the CS76 in the submillimeter. These are SMA observations. And the fact that after subtraction of the continuum, you see an absorption at velocities, at redshifted velocities, indicates that the front material is moving towards the object. This is not means necessarily that is gravitational accretion, but at least there is some motion towards the center of the object, which is consistent with gravitational accretion. So now I will talk about an infold signature, which is more complete than this one. This is an old paper, and this was on the study of the infold signatures for gravitational collapse. This has been widely used. I just want to remember that when you have gravitational collapse, one main characteristic is that you have not only a velocity towards the center, but an acceleration. And this is frequently forgotten, because it means that you cannot derive a single velocity. Intrinsically, you have an acceleration. The fact that you have an acceleration means that the projected velocity along the line of sight will make this kind of closed surface, like egg surface, because when you are going closer to the center, the velocity increases, but the angle of the projected velocity is worse, so you need to go to higher velocity to have the same line of sight velocity. Okay, so if the lines are optically thick, what happens is that you only can see this side of this closed surface, because this one is hidden. And on the blue side, you only have this side. Because this, on the average, is far away from the center, and because the temperature increases toward the center, this is colder and this is hotter, and you get blue-red asymmetry with the blue line with the blue side stronger than the red side. So this is interesting, because something spherically symmetric produces something that is not symmetric. However, this is not a very strong info signature. In fact, if the velocities are small, you can get reverse symmetry. And this is not a good signature, because the line profile does not contain a spatial information. You have a point here of a given velocity, and you have the total integrated flux density. But if you make a high angular resolution observation, you can have a map of this surface. It will be essentially, if the opacity is high enough, a map of the temperature distribution. And then if you make a map, and you will have a cube as a collection of channel maps, the channel maps corresponding to red-shifted velocities, these points toward the center are slightly far away than these other points. So you will have something that will be essentially flat, but decreasing slightly toward the center. And for the blue-shifted channels, you will get something completely different, because here, towards the central points, the points are very close to the center, so you will have a very strong peak. So you will have very different channel maps. The blue-shifted channel maps, the intensity is stronger and centrally peaked sharply toward the center, while in the red-shifted maps, the emission is essentially flat. And there is another effect, because there is a gravitational acceleration. At larger velocities, you will have a smaller surface. So the size of this emission is decreasing with the velocity. Okay? So this is an info signature. We published that in 1991, but we thought that at that time, the interferometers, they do not have the capability to detect that. In fact, this example corresponds to one solar mass protostar, and we think it was too weak to be detectable. However, in the sources that I have shown you previously, which is a very high mass protostar, we were surprised, because we were not looking for that this signature is present. So here is the intensity profiles, the intensity as a function of the project distance to the center. This is not line profiles, these are intensity profiles, the map. We do that by averaging, again, along circular rings in order to increase the signal to noise ratio. And we can see this effect. This is a redshift. This is the 2-2 line, the 3-3 line, the 4-4 line, the 5-5 line, and the 6-6 line, and all show the same pattern. The blue shifted channel is stronger and more centrally peaked than the red shifted channel, whose emission is flatter. And the second effect, as the velocity increases, they are separated by 4 kilometers per second with respect to the center, and these are separated by 6 and this by 9. As the velocity increases, the size decreases. So this is narrower than this one. Okay? So apparently this signature is present in this source, and this is very difficult to imagine another effect that can simulate this effect. So it's much powerful signature than the line profile when you only look for a slight asymmetry between blue and red. And this is found in all the transitions. Unfortunately, the observations were not designed to see this phenomenon, and the channel width was pretty wide, and the central velocity was not exactly centered at the center of a channel. So in fact, these are not exactly symmetric pairs of velocities. Separate 4 kilometers, and there is this 3.4, but it's apparent. Okay, this is the main signature, but we have a model of this object that we did in 2009. And if we compare with the prediction of the model, we see that not only the main features, but also the values, there is a quantitative agreement. This is the same scale, 12 and 12, and there is a quantitative agreement between what predicts the model and what is observed. Okay, so we think that this is a strong signature of info in this source, and we think that with ALMA and this kind of new sensitivity interferometers, they could be obtained in other sources, not so strong, and probably even in low mass protostars. So I think this is the future. This is the to angularly resolve the info signature, not just to look at the spectral line profile. Okay, I will talk about the second region, which is the home molecular core near the W3OH H2 region. Here is the H2 region. This is another more extended H2 region in the proximity, and this is the home molecular core. This is called also the TW object for Turner and Welch, or also it is called as W3OH, H2O, because there is a water measure here. So here is an enlargement. This is a Plateau de Beer observation at 1.4 millimeters, and we can identify in the millimeter observation, which is the gray image, a source here that is called A, another here that is called C, and probably another here that is called B. In the radio continuum, at the free emission, there is a source here, which is source A, and this other here. This has a clearly gel-like structure, and there are water measures with clear proper motions in the direction of the jet in this observation, in this BLBA observation of Alcolea and collaborators. And apparently the jet has also a non-thermal component. So there is a recent observation of this source published by Luis Zapata and Luis Rodriguez from SMA observations, who found several components of molecular outflow, blue shifted and red shifted. This is the home molecular core here, the H2 region, and they identify that probably this molecular flow comes from source A and this one from source C. However, in the SMA observations, if you look carefully, even when Luis identifies this source with the continuum source, with the radio continuum source A, we can see that the submillimeter sources are closer, that in fact there are the centimeter sources. And you can explain by problems in the absolute positions that maybe this should be shifted, but if you shift one, then the other one does not coincide. So we think that probably there are more one object here, and perhaps even more one object here. So I will take this into account in our analysis. those are our VLA observations of the ammonia 4,4 line, and this is the map of the main line. The circles are the submillimeter positions, and the crosses are the centimeter positions. You see that submillimeter positions are closer than between them than the centimeter position. So we think that probably this jet source here is a different object of the submillimeter source A. So this is the main line, and this is the satellite lines. So I do not pay too much attention to this, but my student noted that there is different orientation of the structure. You can see this is the satellite line, and the main line is more horizontal. And also here the main line is an elongated structure, a single elongated structure, and the satellite line has two peaks. Here I put this in contours. It's a bit mazy, but you can see the red are the satellite lines that have this orientation, and the yellow are the main line with this orientation, and the same happens with source C. So we have velocity gradients. It's a clear velocity gradient, and the west part is more redshifted than the east part, and the same happens with the satellite lines. So there is clearly two separate regions, but also inside the same region there is a velocity gradient. So here this is probably related with the jet source, and this is another gradient which is probably related with the submillimeter source A. And the same for source B or BC. I do not know exactly which one, because we do not know if there are one or two objects also here. So we're trying to model the ammonia emission and trying to reproduce these effects. And this is the previous model of the source that was published in the 1999 paper by Osorio, Lizano, and D'Alessio. And note that the spectral energy distribution was pretty poor because they only have 3 data points. And here you do not have constriction, so it can be a much lower luminosity. Now we have more points here because of the SMA observation and the millimeter observation. So in this modeling, they used an envelope of 10,000 AU in size, and they obtain a mass of the envelope of about 80 solar masses and a central star of 16 solar masses. So these are old observations of the source with 4 arcsecond resolution. These observations did not distinguish between the eastern and western sources, or is the whole molecular, so the whole core, as here that it was modeled as a single object. And this is a prediction of this model. So the shape is pretty similar, but here it should be noted, you cannot see probably, but this is 0.3 and this is 0.1. So this is 3 times stronger, the prediction of the model, than the observations. So now we modeled this structure as a structure in folding with a bit of rotation as the Terebai-Shu and Kassen model, because we have this velocity gradient and we have that the structure had some flattening. And this is the best fit model. This is a very preliminary result. It will change. But in this model, this is the temperature, this is the density, here is the centrifugal radius, and this is this increase in density. This is the region where the disk will be expected to be produced. And this is the spectral energy distribution. This is reversed from the previous. This is in lambda, and the previous was in frequency. And now we have more restrictions. We took this as upper limits because we do not know if there is a single source of 2 sources, sources A and C. But this is for the source A, but even in source A, we do not know if the jet source is different. So we took the submillimeter as an upper limit. So this is the fit to the spectral energy distribution. This is the fit to the ammonia 4,4 line. Now we have the same intensity. And this is the parameters. In fact, we have used a smaller envelope with a smaller radius, because now we separate in two objects. The mass accretion rate is similar. The mass of the envelope is smaller. It's 15 solar masses, and previously was 80 solar masses. And the mass of the central star is 3 solar masses. We play it very much, and we are still playing with this, but apparently this is a robust result. This is constrained by the line width of the satellite lines. If you make this mass higher, then the rotation velocities near the star are very high, and the line become very broad, and you cannot reproduce the line profile at all. So even when it is well known that this is a high mass protostar, we found a mass of 3 solar masses. What happens here? Well, we have still 15 solar masses in the envelope. We interpret this as this is a young high mass star, which is accreting at with a high accretion rate of 10 to the minus 3. So it has a large luminosity. So this is a baby high mass star, but still does not accrete the whole mass, so it appears as a low mass, but has the properties of a high mass protostar. And in fact, we have found that in other sources. If you remember, the main line was like a single source, elongated source, and there was a change in the orientation when you move to the satellite lines. And then it appears this double peak in the satellite lines and not in the main line. So my student, what has done is he built a radiativity transfer code, and he put the equation of the Terevai-Schoen-Kassen model, and now he's trying with the sheet collapsing equation of Lee and collaborators, and try to reproduce this, the intensity of the ammonia emission, of course the spectral energy distribution, and if you have something that is rotating and it has different inclinations, and you have to reproduce the velocity gradient, the shape of it, you finally are constraining all these things. And in fact, he finds the velocity gradient in the same sense that is observed, and also because he has the velocity, and it depends on its inclination towards the sky or towards the observer, he can predict which is the red-shifted lobe and which is the blue-shifted lobe. And these are in agreement also with the observation. And this is the kind of thing he's working. This is just one of the models. This is not the best one. This is not the last one. But just, this is one, I wanted to say that using all these constraints, you can, for example, one thing that is interesting that if you take this velocity gradient and you calculate the central mass from this velocity gradient, you do not find the mass that is in the model. So it means that just taking the observational velocity gradient and just using the Keplerian equation and calculating the central mass is not an accurate way of calculating the mass if you have this temperature, velocity, and structure gradients. So it was my last slide, and this is our conclusion. We have carried out high angular resolution observations and modeling of 2 hot molecular cores. In both regions, we are able to fit simultaneously the spectral energy distribution and the ammonia emission, and from this we can constrain very much the physical parameters of the regions. And in the case of G31, we have found strong indications of gravitational inflow, which is angularly resolved in our channel maps. And as far as I know, this is the first time that this has been found in a stellar object. Thank you.
Guillem, these velocity profiles are really nice, that you can resolve them. I think it's very, very nice result. I just wanted to ask you, in the case of TW water, the disk in the Terry-Schuenkassen, is it perpendicular to the observed non-thermal jet?
Yes, it is perpendicular.
The model?
Yeah, but it's the same. The model is also in agreement. So this is optically thick. So here there are these optical depth effects that make this kind of rotation. But the true position of the structure is this one. So the outflow is like this direction. So they are perpendicular. But we have not modeled this as a disk. We modeled this as an infalling envelope, because the distinction we made is that a disk is something that is rotating only, and an infalling envelope is something that is rotating and infalling. If you only put rotation, you cannot reproduce the ammonia observations. You need to put also a component towards the center, infalling.
Yes, I meant to say that your model has an axis of angular momentum, and this axis has to be in the direction of the...
Yes, this is...
But then you would predict that there should be a disk there. The rotational support.
Yes.
With ALMA or something.
Yes. In fact, there is. So here is the centrifugal radius. So for this centrifugal radius, which is 500 AU, we expect a disk of about 500 AU. But this does not mean that that in the ammonia that we were modeling, the main emission is from the envelope. In ammonia, we think we are not seeing almost nothing of emission from the disk.
Yeah, it's very interesting. You use singular logotropic spheres to do your modeling. That it requires some kind of non-thermal support. If it's turbulence, of course, it's related to the line width. Did you put the non-thermal line width into the modeling when you do the radiative transfer?
For G31, the first source, this one, here this is the non-thermal component, turbulent, which is calculated self-consistently from this singular logotropic model that Susanna and you made. And this implies a magnetic field which is the order of, I think, 1 microgauss or 0.5 or so. This is interesting because in the measures of the polarization with the submillimeter array, they derive the same value of the magnetic field that milligauss. And for the second one, this one, we did not did it in the width in a self-consistent way. We just were trying different turbulent widths. So my student tried with a constant turbulent width and with something that's changed, like in the case of the SLA's collapse. And finally, he told me that the best fit was this kind of line width that increases when the density decreases, as in the singular logotropic sphere. But in this case, was not put self-consistently.
These info mapping signatures are very important. And of course, people would like to see many of these many sources done this way. So do you think that is a program that will, let's say, try to find this in many sources, in a dozen sources or so, is feasible now?
Well, in principle, I think with ALMA, this should be possible. In fact, we sent this a proposal for ALMA, but probably the referees did not understood our aims very well. I think the first step is try to confirm this in this source. In fact, I think it will be easy to confirm here. In other sources, it will be more difficult because this is a especially strong source, and we did this in the centimeter regime. When we move to the sub-millimeter regime, there is an important factor that should be taken into account. That is the core itself, the dust from the core itself emits in a very strong way. So here in the centimeter, we have only the line emission, but when we move to the sub-millimeter, we have to reconstruct this and take into account the sub-millimeter emission, the continuum sub-millimeter emission of the core itself. But I think it should be possible in the next years.